Hello, everyone. My name is Tania de Monte Gonzalez. I'm a PhD candidate at Michigan Tech University, and today I will be presenting the research in parameter varying hydrodynamic modeling of a single vane in a variable geometry oscillating surge wave energy converter. I would like to thank you all for being here today, and I would also like to thank NREL, who was a big part of this project. The biggest motivation behind this work, so I'll move the camera a little bit. The biggest motivation is the negative effects that traditional energy sources are causing to the environment. It has caused this big transition towards renewable energies. And you can see from this image here, marine energy resources have a huge potential for powering. This particular case is for the US, where it can power it could generate about 57% of the total energy that was generated in 2019. That is a lot of energy, and different devices have been developed to tap into this resource. That's what we call the wave energy converters. And the one specifically I will be talking about today is the oscillating surge wave energy converter. But why are we not seeing more of these devices in the ocean yet? It's mostly because it's expensive. The cost per kilowatt hour produced is very expensive. So most of the research nowadays is focusing on how can we reduce these costs. So here we have the RM5. This is the reference model 5 of an oscillating wave energy converter. So you can see it's a structure that has a flap that it oscillates as the waves pass, and this generates the opportunity to harness the energy from the waves. And here on the right, you can see a plot for the cost associated with these devices. And on the laser pointer, if we just have one device, here's the first bar, we see that there are three main costs associated with it. These are the permitting and environmental compliance. That's this one. Then we have the device structural components, and then we have the installation cost. These are all very big costs, but as we scale up in the number of devices, they start to reduce the cost. All of them except for this one in blue, which is the device structural component. Because this is a big cost, even if you scale out the device, researchers at NREL are coming up with new ways of reducing the structural cost of the components so that we can make cheaper ones. So this is the variable geometry OSWEC that NREL researchers have been working on. It consists of this oscillating wave energy converter, but it has these vanes that are controlled so that they can be fully open or fully closed or at different positions, depending on the sea state. So for example, if you are in power production mode, you're gonna have the vanes to be fully closed. And so you take full advantage of the wave and capture most of the energy that you can. But if the waves become a little extreme, where you go to survival mode, then you can open the vanes, and that will reduce the loads at the foundation of this device, and therefore you can make foundations that don't have to be super robust, and therefore making it cheaper. So a lot of research has been done on this sort of VG OSWEC, but mostly when it's modeled as a static configuration. So it's modeled with either the flaps fully open or fully closed, or just at a specific angle. The main objective of my paper was to have a model that would capture the variation in the hydrodynamics as the flap is, or sorry, as the vane is moving. And so all I'm doing in this work, it was a preliminary study. So all I focused was in just a singular vein of the device, and I am not considering the degree of freedom of the main flap. So for this research, the main flap is considered to just be stationary at the 0-degree angle configuration here. The way I approached the modeling of this single vein was very similar to the way that traditional OSWECs are modeled. So we have, this is the equation of motion that I'm using. And we have the added mass at infinite frequency here. This is part of the radiation waves. We have the hydrostatic coefficient. We have the radiation impulse response function here, the excitation moment. And then we have here at the end where we typically have the power takeoff dynamics. In my case, I just have a rotational spring and I'm calling it Km. This is the stiffness coefficient, and I'm just calling it a mechanical spring and not PTO because the main purpose of this spring is to just keep the vein from fully rotating, and it's not meant to be harnessing any energy, maybe in the future, but not for this preliminary study. And something you may notice on this equation of motion is that these coefficients are dependent on the flap or the vein position, and that's theta. So theta, when the vein is fully closed, it's considered 0 degrees, and the vein is fully open is considered 90 degrees. So these are the hydrodynamic coefficients that are going to change as the vein position changes as well. I have 4 different models on this paper. And the first one is the linear time invariant. For this one, the flap is considered to be fully closed. The vein is fully closed. The second model is a coarse parameter varying, where, as you can see here, I have the vein in different positions. At each of these positions, I calculated different hydrodynamic coefficients. This coarse parameter varying model is just jumping from one coefficient to the other coefficient as the vein is rotating. So that's why I'm calling it coarse. Then we have the interpolation parameter varying, where I have interpolated the coefficients across the different angles of the flap. And the last one is the curve fitting parameter varying, where I have fitted a curve across the different angles of the flap. And I'm going to compare all those 4 models at the end when I'm showing the results. So here we have the added mass and the hydrostatic coefficients. So here's the added mass moment of inertia. As you can see, from 0 to 20 degrees of the vein is a little bit more refined, the amount of data that I got for the hydrodynamic coefficients that I got for this range, and then it becomes more coarse because the hydrodynamic coefficients changed a lot more within this range. So I had to do a finer resolution in that range. In this case, I'm only showing the coefficients from 0 to 90 degrees because these coefficients are the same for the negative angles. So for example, at 20 degrees, the added mass moment of inertia is going to be the same as the negative 20 degrees. And so I only calculated it for the positive angles, and then for the negative angles, I just mirror the results. You can see also here the interpolation and the curve fitted model, and they represent these curves very well. Now, the radiation damping was a little bit more challenging. I represented the convolution using a state space model. And the state space model, I then turn it into a transfer function. And the transfer function has a number of coefficients in the numerator and a number of coefficients in the denominator. What I did was I got a transfer function model for each of those vein positions, and then I interpolated across the coefficients of the transfer functions. So Here you can see this is one of the coefficients. This is the 7th coefficient. I did a 6th order state space model. I had to keep the order of the state space models consistent for all the different flap positions so that I could do this interpolation. And here you can see it's also symmetric around the 0 degree. So for the 20-degree angle, it's going to be the same as the negative 20-degree angle. So for this one, I just calculated it for the positive side and then mirror it to the negative side. And you can see here the interpolated, the discrete data, and the curve fitted data. And now for the excitation moment, this one was a little bit more challenging because this one is not symmetric about the 0 degree angle. And that is because the phase of the excitation moment changes as the flap is either in the positive configuration or in the negative configuration. So in this case, I had to create this excitation moment surface. This is something that will have to be done ahead of time in the simulations. And I use the interpolation method to create this excitation moment. I did not do any curve fitting of this. The curve fitting of this excitation moment will be part of my future work for this project. All right, so for the results, we run different regular waves, and you will see I'm gonna show 3 cases in this presentation. The first case, the first and second case just change in the wave amplitude. So I increase the wave amplitude. And then the third case shows the same wave amplitude as the first one, but with a higher frequency. This is mostly to identify how these 2 wave characteristics affect the hydrodynamic coefficients and the modeling of this. For the linear time invariant, I am considering the flap to be fully closed. And then also I have compiled all of the hydrodynamic forces into what I call, the hydrodynamic torque. I call it the hydrodynamic torque here. And that's what you're gonna see. This is the summation of all the different torques. All right, for the first case, I'm gonna move my camera over here. For the first case, we have a small frequency and a small amplitude. And then the mechanical spring, you can also see is 5 kilonewtons meter per radian. You can see here in blue is a linear time invariant. And then the other 3 are the parameter variant models. The flap is rotating about 15 degrees to 10 degrees. So it's not rotating a lot. And in this case, you can see the linear time invariant is not all that different than the other 2 modeling methods. We do see here, for example, in green is the coarse model. This one we see has like this very high frequency. This is because the coarse method is not, it generates this high frequency content because it's kind of jumping between coefficients. There is no smooth transition. And I mentioned also that between the plus and minus 20 degree configuration of the vane, the hydrodynamic coefficients change a lot. So because of that, we can see this high frequency content in the coarse model. But in the interpolated and curve fitting model, that is fixed. It looks very nice. Now, this case, they're very similar, but then if we go to the second case, where we increase the amplitude, we see now that the linear time invariant model really overestimates the flap rotation. It also overestimates the total hydrodynamic torque, and the total mechanical torque needed to keep the flap from fully rotating would also be higher in this case. It will be predicted to be higher, even though we might not need it. And then the last case was increasing the frequency, is also showing a very big discrepancy between the linear time invariant and the other parameter varying models. And this really highlights the necessity of having this parameter varying model. It does make a big difference. And that's all that we wanted to see with this research. I'm a little over time, so I'm just gonna jump to the end of the conclusions. Linear time invariant models were okay for very small motion, but as the waves get bigger, it will be better to have a parameter varying model. The interpolated method and the curve fitting models, they both fit. They were both great models, so both could be considered. Thank you so much. And here is my email in case you have any follow-up questions.